Statistical Rethinking, second edition, chapter 15. We're in the medium difficult questions, question 15M5. So, if you're going to run any of this code, make sure that you've run the first, blocks up here to install and load all of the necessary packages. And here we are. Okay. So we're going back to a model presented in the chapter, the singing bird model, which is model 15.9. And we're going to compare the posterior estimates of cat presence. This will make sense in a second if you're a little bit need a little bit of a refresher on the model, to the true simulated values. And then we want to know how good the model is at inferring the missing data and come up with some ways to change the simulation to improve our inference. Okay. So the basic setup is that we simulated some data, which is presented here, where we are measuring the number of notes, that are sung or sang, whatever the proper grammar is, by songbirds, I guess, out in the wild or at least, around neighborhoods. Not really wild, but and we are modeling that as a function of, well, here's our linear model for it right here, some baseline value plus some effect of the presence of a cat. Okay, and so we have the presence of a cat being governed as a Bernoulli random variable, okay, with probability k, where k is set to 50%. Okay. Now, because cats are very stealthy, we do not, sometimes we do not feel confident that we have adequately assessed that there is no cat, right? So if we don't see a cat, it's either because there isn't a cat or because the cat was hiding and we didn't see it. Okay. And so we also have this variable that that tells us how likely it is that we don't know the true cat status, right? There may or may not be one there, but we don't know. Okay, we can't feel confident. Okay. And so therefore, our actual observations are a subset of cat, whether or not there was a cat there. Okay, and in this case, we replace the cats that we replace the observations that we did not see with this value of -1. And we do that because this is an invalid value in the model. I think the book uses -9, but I'm going to use -1 just for some reasons that aren't really important here. Yeah, okay. So we have our data all packed in this nice little list here called DAT, and then we run the model. I guess it's important to say that this is all copied and pasted from the book. Although I have rearranged some things and added some little notes here to kind of help refresh your memory as to what this code is doing. Okay, and so we also have the model here, again copied and pasted from the book. And I guess what's important here is that we have two scenarios. We have the number of notes when RC equals 0. Okay, now when RC equals 0, that means that we know the cat status, right? RC is the probability of not knowing the cat, okay, whether or not the cat is present, okay? So RC equals 0 when we know the cat status, and then RC equals 1 when we don't know the cat status, okay? But when you look at, RC equals 1, it's this big, ugly expression here. And the book explains all of this. It's just putting all of this on the log scale for 1, and then it's looking at the probability or the number of notes under both circumstances, when there is a cat and when there is not a cat. Okay, so that's what's happening there, and I won't march through it. I think the book does a relatively decent job of doing that for you. Okay. Okay, and then we have our linear model for the parameter, for log lambda in this case, and we have our priors. Okay, so I've already ran this model so that we don't have to sit here and watch it. And now this is really kind of the meat of the problem, is we need to compare the model's predictions for the presence or absence of the cat to the raw data. Okay, so you can look at my code here, but I've partitioned observed observations and observed cases and unobserved cases here. Okay, based on the output of the model. Okay, so for the observed cases, we have whether or not there was actually a cat present versus the probability predicted by the model of there being a cat present. Okay, and this is what we get. So the size of the marker represents the size of the uncertainty, right? So bigger markers mean more uncertainty. Okay, and so this is what we get. And so with the observed ones, predictably, there's quite a bit of overlap. And, I guess it's doing a decent job in that, on average, the one, where a cat was observed, the probability is higher. I guess that's a good sign. And then we go to the unobserved, right? To the unobserved cases. Remember, we know the actual values because we generated the data in this case. And again, it seems to be doing a decent job, right? When there actually was a cat there, the model's doing a pretty good job of picking that up. Again, with quite a bit of overlap, but yeah. So now, okay, so I just said, that the model seems to be doing a decent job, but in a way that's kind of a that may not be an appropriate thing to say because we can only say if it's doing a good job compared to other models, and we don't have other models here. So really, to really make that a better statement, we should say, how it's doing compared to some other model. Okay. Now one of the things, let's say that we had another model. Now one of the things that we might do to compare the models is to measure how far away each of the markers were from 0 if there was no cat, or 1 if there was a cat, right, from the appropriate value here. Okay, and so that's what I've done here, and then we could do something like sum the absolute difference between the probability versus 0 or 1, which is what this value is here, and then we could even plot it, right? So for the different for the different values of the probabilities here, we could measure the distance from the true value, right? And so that's what this is measuring right here, right? So if it's on the red line, it means that it's that the predicted value is perfect. It's 0 or 0 or 1. None of them are 0 or 1, but some of them are reasonably close. And we could compare this amongst different models and see which one was doing better. Or we could compare this number, which again is kind of the sum of the absolute values of the differences between the prediction and the actual value. Now the last part of the question, up here is, can we change the simulation to improve, the precision of the inference? And so when I read this, it says, how do we change the simulation? Which, refers to this part, not the model, right? We could try different models, but it's asking how would we change the simulation? Well, that seems like a little bit of a weird question, but, there's some obvious answers here. And two of the most basic answers here are, we could increase the sample size, or in other words, the number of houses, or when we were generating the data, we could pick a different value for say k here, the probability of there being a cat, or a different value for r, the probability of knowing whether or not knowing the cat status. So okay, but anyway, I'll call that good.